Thank you. I want to thank the organizers for coercing me into giving this talk. No, I'm actually, to use some baseball lingo, pinch hitting for Clayton Webster, who was supposed to be giving this talk and unfortunately couldn't come. So on short notice, I tried to put a talk together. So it's going to be very disjointed because I didn't have time to polish it. I didn't have time to put any references and stuff like that. But bear with me. So yeah, there is a town called Uncertain, Texas. Okay, so well, first of all, I have to define what uncertification means to me. I've given talks on uncertification at a couple of places, and which there were statisticians in the audience, and they came up to me afterwards and said, "What's the big deal about UQ? That's what we statisticians have always done," which is true, of course. So that's one definition. But here's for the purpose of this talk, this is my definition. Because UQ does not have to be done probabilistically or statistically. It can be done many other ways, several other ways. But for me, UQ is a task of determining statistical information about outputs of a PDE, given statistical information about the inputs. So for me, U is a solution of the PDE. F of U is an output of interest. Some people actually refer to that as a quantity of interest. And to me, the quantity of interest is statistical information about the output, F. So I just want to make precise about what I mean by this terminology in this talk. You may have different. One of the themes of this talk is that not only is there different language between math and statistics, there's different language and different definitions used within the math community for different things. So one way or another, I'm going to assume that we parameterize the problem. So I'm talking about parametric uncertainty. And here's the first problem with probability and statistics. PDE people are not willing to give up the notation X for spatial variable. So we can't use X for random variable. So we're not willing to give that up. I mean, we give up a lot, but we got to draw the line at X. So the random variable is going to be Y. Vector random variable is Y. The other thing we do give up is omega, because omega in the PDE community is very often used to denote a spatial domain, but we all know that probabilists use omega to denote something else. So we gave that up, so I called the spatial domain D. So and we're going to consider evaluation of statistical integrals. So we all know what that is. We have some integrand G of U. You integrate against the PDF, and G could corresponds to the statistical information you want about F. So if G of F equals F, you have the mean, so forth, so forth. We also consider building surrogates, and there's different ways to build. You can build a surrogate for the solution of the PDE. You can build a surrogate for the output of interest, and there's two ways to do that. You can build a surrogate for the thing that you want the statistics based on the G, which is based on the statistics you want about F. And there's important to look at these different ones. I'm not going to talk about it, but for example, if you're talking about finding probability of an event, we all know that is basically an integral of an indicator or characteristic function, which is not smooth, but it may be that the solution of the PDE or the output of interest F is smooth, so you can build good surrogates for that, and then you can use your sampling scheme to figure out what the relative volume is of where for risk assessment. So for most of this talk, you don't have to know anything about PDEs. So all you have to do is, when I say solution of a PDE, that's what I say, but you hear function evaluations are very expensive. So that's the setting we're talking about, basically from a statistical / probability point of view. Function evaluations are very expensive because they're solutions of a PDE. It involves solving a PDE. There's one thing that maybe I should point out about PDEs, because not everyone may know that. By the way, almost everything I say is going to be known by almost all of you. So you can wake up for the small part that you may not know. But some of you may not know what a Galerkin method is. So let me just give you an example. You consider a PDE. There's a PDE, divergence of A grad U plus CU cubed, etc. So what do? We multiply the PDE by a function V. We integrate the result over D. We apply Gauss's theorem to move one derivative from U over to V, and we apply the boundary condition, and we obtain this equation at the bottom here. So a Galerkin method for the P is defined by choosing an appropriate function space X, and then seeking a function U in that space that satisfies this equation down here for all the so-called test functions V in that space. So this is an example of what is referred to a weak formulation of the PDE. It's called weak because for the PDE to make sense, U has to have two derivatives. For this integral formulation to make sense, U doesn't even have to have one classical derivative. It has to have one weak derivative, whatever that is. We can explain that. A lot of what I talk about, I'd rather talk about over a bitter or a single malt, so we can do that. So the weak formulation, so correspondingly, U is called the weak solution of the PDE. This was really a big advance in PDEs to the notion of weak solutions. Comes from 1930s. And here's where Sobolev spaces, which are these mysterious things to some of you, become very useful, because for this PDE, the X is a Sobolev space. That's all I'm going to say. So a Galerkin approximation is done by putting H's everywhere. In our weak formulation, you choose a finite dimensional subspace of X, and then you ask this weak formulation to be satisfied. You look for a solution in that subspace, and you ask it to be satisfied for all VH in that space. Spectral Galerkin methods means that SH consists of orthogonal polynomials, trigonometric polynomials, or others. Phi-element methods, the basis consists of piecewise polynomials defined with respect to a grid, where a piecewise polynomial means it's a polynomial in each grid cell, and it satisfies approximate continuity requirements across cell faces. So, okay, the last talk was very good to me, because I was very perplexed about what the difference between a simulation and emulation was, and that was clarified. But so before that, I went to the OED and figured out what looked for the definition of simulate. So here are to pretend to be, have, or feel, or imitate or counterfeit. In other words, simulate is to cheat. But 2 definitions down, it just says produce a computer model of a process. So, for my community, simulation is you take a infinite dimensional model, like a partial differential equation, and you make it into a discrete model, which you can put on a computer, and that's a simulator. Then I looked at both OED and the Merriam-Webster dictionary for emulate, and they're very close. And one of the definitions is to intimate or counterfeit. So again, emulate is also to cheat. But down a ways, the third definition says to especially to imitate by means of an emulator. Oh, okay, now we have to define emulator. Well, I guess they don't know about circular reasoning, because if you look up emulator, it says one that emulates. But the second definition is interesting to me. It says hardware or software that permits programs to be written for one computer to be run on another computer. And that same definition is in the OED. So that's not what anybody here thinks an emulator is it? But anyway, that's what an emulator is, and now I'm really confused, since I believe in those dictionaries. So, what type of, well, let me quickly, so what type of uncertainties do we deal with? We deal with random parameters, and these are parameters that appear in the model, you know, in the model itself, such as chemical reaction rates or Young's modulus or things like that, which may be uncertain, and so they're parameters. And then there are parameters that come from parameterizing random fields. So we have, and there are two kinds of random fields, as we all know: white noise, for which the value at any point at any instant in time is picked out of a PDF and independently, and then colored or correlated random fields, they're not picked out independently. You have some covariance or correlation function that associated with the field. So here's white. How do you approximate white noise? Well, here's one way. You have a grid. We have a grid. This is the grid we use to solve the PDE, and then we just sample at every grid cell. We have a piecewise constant approximation, and we just sample in each grid cell independently from a PDF, and that's grid-based approximation to white noise, and you can do it in time also. And here's the 1D results. This is a white noise input. We either put it as the right-hand side, additive noise, or have a multiplicative noise where we multiply the solution U by white noise. And the thing you get out of this, which will be important in the next slide, is that the solution is much smoother than the input. Why is that important? Well, before I say that, white noise fields can also be approximated by finite expansions in terms of global and piecewise polynomials. And this is what Norbert Wiener did for Gaussian random fields using Hermite polynomials. And it's for Gaussian white noise, which is, and he termed this polynomial chaos. And he was really trying to model chaos, white noise forcing on a PDE, white noise right-hand side in a PDE. So let me say a few words about white noise. I never understood white noise because white noise has infinite variance or physically has infinite energy. So white noise cannot exist. The correlation function in 1D white noise is proportional to the delta function, so it doesn't have finite second moments. Second moments are infinite, so that's why the variance is infinite. So why can we compute when white noise inputs are present? Well, we discretize the white noise. It turns out that, like for instance, the grid-based method, the variance of discretized white noise is 1 over, there should be an exponent there, but basically it's proportional to 1 over the volume of the grid cell. So it's finite. So the solution of elliptic and parabolic PDEs are smoother than the inputs. They have finite variance. So what does convergence mean for approximated white noise? It can mean anything pointwise because you're trying to converge to the delta function. It's covariance. So you can only converge. You can converge the correlation function and expectation, and you notice that as the volume of as you refine the grid, the variance increases, and so there's no notion of convergence because you're converging to something that the variance is infinite, and this thing is getting bigger and bigger. So white noise is sort of to me a little, I don't know why everybody uses it because, okay, it's infinite energy. So noise fields are not so easy to discretize because of the lack of independence. So the mean and covariance of the field is known as, for instance, for Brownian motion or Wiener processes or Einstein-Uhlenbeck processes, or you assume it or have some other information and you know the correlation function. Then you can approximate a colored field by various different ways I list there. The most popular way is the Carhuning-Loewe expansion. KL expansions are based on eigenpairs of the covariance function, and in practice one truncates the expansion. One also uses, you also usually approximate the covariance function because you can't find the eigenvalues. You only can find the eigenvalues of a discretized covariance function. So there are two sources of error here, one truncating an infinite expansion and one approximating the covariance function by a discrete covariance, by a matrix basically. Now why are KL expansions wonderful? So they represent a random field for which only the mean and covariance are known in terms of parameters. So you can now evaluate that random field and approximation to random field just by choosing parameters. So that's a wonderful thing. You don't have to worry about the covariance anymore. And the second thing is that you took a correlated random field and now you represented it in terms of uncorrelated parameters. So those are two wonderful things. Excuse me. But do we really know how to evaluate a random field? Correlated random. What's the problem? The problem is that, as we all know, independence implies uncorrelated, but uncorrelated does not guarantee independence. In fact, it can only be guaranteed in a multivariate setting if you have more than one parameter. If basically you have a multivariate or spherical, or basically if you have a distribution that a PDF that factors into one-dimensional PDFs. So this fact is ignored by my community. So other PDFs are used even though there's no guarantee that KL will give you independent parameters. So you might have some additional information. And if you want to do this right, you have to use CDFs and inverse CDFs to get from your from the CDF from a PDF from the thing that's not Gaussian to a Gaussian process, and then you can do the IID sampling. But nobody does that as far as I know. The curse of dimensionality you heard about. The computational costs grow very fast as the number of parameters and the degree of approximation increases. And of course, us in the numerical analysis community are used to that sort of stuff because we know that it's more expensive to solve a PDE and a 3D PDE than a 2D PDE or a 1D PDE. But we just go up to 3, or some people go up to 6 if they talk about certain PDEs, 6-dimensional PDEs if they work in phase space as well as in physical space. So a lot of numerical methods that we use that are good in 2 and 3D are not so good in even 5 or 6D. And that's what the curse of dimensionality is about. So I'm going to talk about discretization with respect to the parameter space. So stochastic phi element methods, and I'm going to talk about phi element methods here because it's just, but a lot of this can be said for other methods. Refer to methods where spatial discretization is effected using phi element methods. A stochastic Galerkin method is one in which the discretization with respect to the parameters is also effected by a Galerkin method. And polynomial chaos methods are a particular type of SGMs. I put polynomial chaos in small letters because I don't really want to use that term. I hate that term. But, you know, you have to know what polynomial chaos, because there's a million papers on polynomial chaos. Another class of stochastic phi element methods, of course, are stochastic sampling methods, Monte Carlo, etc., stochastic collocation, quasi-Monte Carlo, etc. So beating the curse of dimensionality. So what's the problem here? So stochastic sampling methods, you have to solve PDE for many parameter sample points. For straightforward stochastic Galerkin methods without some intervention, you have a huge decreased system whose size is the product of the stochastic and phi element degrees of freedom. And these are manifestations of the curse of dimensionality. But things are even worse in the PE setting. We're doubly cursed, because the dimension of the spatial approximation is also large. That's what makes function evaluations expensive. For stochastic sampling methods, we have to do a lot of expensive PDE solves. And for stochastic Galerkin methods and their straightforward guys, means you have a huge single system to solve. So not surprising, there are two big armies of researchers attacking this problem. Army A tries to do something about reducing the number of stochastic degrees of freedom. They develop better stochastic sampling methods that result in the same accuracy but require fewer sampling, sparse grids, etc. Army B tries to do something about reducing the number of spatial degrees of freedom so that the cost of obtaining a sample of a function evaluation is reduced. And that's sort of the subject, or one of the subjects of the third workshop that we're having here. Well, the note is that if you try to reduce you try to build a surrogate that reduces the cost of finding approximations to your solution or your PDE or something like that, you usually have to first do some expensive solutions. Okay, we take a break by a couple of quotes, and then we'll get, we're going to have trouble. Good. Okay. Stochastic Galerkin methods, I think I only have one slide. So I already said what that is. It's so what is that? So the idea is that you now have a function of the spatial variable x and a random vector y who lives in a certain domain. And it's natural to think of this, just think of this as one solution of d plus n variables, where d is the number of spatial variables, 1, 2, 3, or more, and n is the number of random parameters. So we think of that, and we have a function space for x that we described before, and we have a function space for z, which is usually chosen to be a weighted LQ space. So it has, and Q is the number of moments you want to make sure that your solution will possess. Usually, most often, if Q is 2, you just do L2. And now the black is what I had before, and now I just wrap this around an integral over the parameter domain gamma, or I take the expected value of the weak formulation I had before, basically. Multiply by rho and take the expected value and get the expected value. But now I'm working in this huge space x cross z. So if we discretize in parameter space using a basis consider of global orthogonal polynomials, we get what is referred to as polynomial chaos approximation. So polynomial chaos equals global orthogonal polynomial approximation. So that's what it should be called. At least for a numerical analyst, that's what it should be called. Here's the bad news. So one nice thing about orthogonal polynomials is they have a hierarchical structure. The nth orthogonal polynomial in 1D is of degree n minus 1 or whatever, depending where you count at 0. So the hierarchical structure allows you to pick, instead of taking in multi-D, instead of taking the full tensor product of all the possible combinations of one-dimensional polynomials, it allows you to just pick those ones that will give you total degree interpolation, give you things inside the Pascal triangle. And here is the cursor dimensionality. There was a table put up yesterday. I'm more modest. I didn't go up to the number 9. I only went up to the number 3 and 5 here. And this is what happens if you use a total degree basis and a full tensor product basis. Well, tensor products are really bad. Total degree bases are good only compared to tensor products. They're bad also. So just a very modest thing, 10 parameters. Your degree of your polynomial is 5. A lot of people think they need higher degree. These are global polynomials. You want maybe more than 5th degree polynomial. But you're already at 3,000 degrees of freedom. And if you think you can do 100 parameters, degree 5, Well, good. 96 million. You need 96 million random parameters to do that. So the cursive dimensionality is in stochastic Galerkin methods in their straightforward form. You have to solve a huge system. I'll get back to mention the not straightforward form. Another break. So that's stochastic Galerkin methods, and the other thing we want to talk about is stochastic sampling. So Monte Carlo methods, and so first I talk about Monte Carlo methods and other simple sampling and averaging quadrature rules. So UH denotes a spatial approximation to our PDE, and I wouldn't bother with time, but you can throw in time if you want. So let's assume the random parameters appear in the coefficient of the PDE, the A, remember, and G, remember, is an integral in our which depends on the output of the PDE, which we integrate to get our quantity of interest. And then of course we have to approximate UH. We have to approximate U as a solution of the PDE, so we make an error there, corresponding approximation of the quantity of interest. And so what's the Monte Carlo method? There's Monte Carlo. And I think Rob's talk on Friday is going to do this in greater detail, so I'm not going to spend a lot of time on this. Well, you know what Monte Carlo is 1 over, you just average your sample, you average whatever you're integrating over random IID samples. And there are two sources of error. There's a spatial approximation. We're not really doing the quantity of interest. We're doing an approximation to the quantity of interest. And then there's a parameter approximation because your Monte Carlo doesn't give you the exact value of the integral. And this is what Rob is going to talk about, so I'm not going to belabor this. But here's what happens, just what the error happens and the cost of Monte Carlo. So Monte Carlo has a great virtue that the convergence behavior is independent of largely independent of the number of parameters. It also has a great fault that the convergence is very slow. It's 1 over the square root of the number of parameters. It has another great strength that it's almost universally applicable. It doesn't care what the smoothness of your integrand is. But that's also one of its great weaknesses, that if your integrand happens to be smooth, it doesn't take advantage of that smoothness. So, but here to illustrate one of its great strengths, here's a Monte Carlo approximation of an integral of a discontinuous function. And you see that if you do enough samples, you get a small error. So that's nice. I put this up because I'm going to compare it with something else. So its strengths and its simplicity of implementation account why I said beyond Monte Carlo, because in practice out in the engineering community and other communities, that's what people use more than anything else by far. They use Monte Carlo approximations. But its weaknesses account for what we all do for a living, which is try to beat Monte Carlo. So the first thing you have to do is make sure you beat Monte Carlo, and in a lot of papers that's what people show. You know, oh, I can beat Monte Carlo. They don't show that you can beat somebody else's method, but you can beat Monte Carlo. So that's good. So improvements. So here's quasi-Monte Carlo, not quite Monte Carlo. We consider, so again, we consider simple sampling and averaging rules. So evaluate G at a bunch of points, and then just average the result. And of course, I talk about this because other people have talked. There's zillions of different ways to do this. People have come up with, some of these have been mentioned already, some Sobol sequences, and so forth and so forth. In general, these improved rules have better rates of convergence. Some of them, for example, have converged like 1 over q, except for this pesky logarithmic factor. Unfortunately for large n, log q grows a lot faster than q. So that gets you into trouble anyway. It's not necessarily better than Monte Carlo, although people have ameliorated that situations. There's multi-level and multi-index Monte Carlo methods, and that's what Rob is going to be talking about on Friday, so I'm not going to say almost nothing about that. And global orthogonal polynomial can be done in a non-intrusive manner. In other words, you don't have to multiply the number of degrees of freedom by the probabilistic and spatial degrees of freedom and solve one huge system. You can do, but I view that as a sampling approach, so I put it in here, because eventually you have to do sampling. So there is a value of global polynomial approximations which can be implemented in a sampling approach, in a sampling context. And the others I'm not going to discuss, because that's what I'll leave it for you to listen to Rob. So another little break. So, okay, so what's left? So stochastic collocation methods. What is stochastic collocation? Well, stochastic collocation is stochastic sampling. It's synonymous basically, but it's now become popular to talk about stochastic collocation for as method as pertaining to a specific kind of deterministic sampling. And these are sparse grid, so-called sparse grid, for instance in quadrature, sparse grid quadrature or sparse grid interpolation. So there are many quadrature, we all know quadrature rules in 1D. In 1D, if you have a smooth integrand, you use a Gauss rule. So in a hypercube, you can define, as we already did, take tensor products of one-dimensional rules. But we saw there's an explosive growth in the number of quadrature points, for example, or interpolation points, if we use tensor product of quadrature rules. So there's a tensor product of points. So what are sparse grids? I'm not going to say much about them, and the reason I don't have to is because you don't have to know anything about sparse grids to use them, because there's all sorts of really good software out there that will give you the sparse grids as a black box, and you don't have to worry about where they came from. But what are sparse grids? Well, the sparse grids were originally came from somebody named Smolyak, a Russian mathematician, and I looked up Smolyak on the web, and I have some images for Smolyak. These are all Smolyak, and not the Smolyak who did sparse grids. So what is a sparse grid? Well, you take your tensor product, and there's a recipe for judiciously removing points from that tensor product grid, or quadrature grid or interpolation point grid, that preserves the accuracy, which gives you the same accuracy as a full tensor product grid, but with much fewer points. And the number of points, unfortunately, is a lot less than the tensor product number of points, which for n parameters and degree m, it gives you that. But it's bigger than the total degree points, which is a binomial coefficient. So still lots of points. But this is sparse grids. And I'll just give you a picture. Here's sparse grids. So if you fill in all the dots, all the empty spaces, you get a tensor product grid. But that's a Smolyak grid or a sparse grid that gives you similar accuracy. And if you know something about your parameters, for instance, if they come from a KL expansion, you know that the eigenvalues decay, so the importance of the parameters gets smaller and smaller as you increase their index, because they're multiplied by a smaller and smaller coefficient in the KL expansion. So if you know something about the anisotropy, you can do anisotropic sparse grids and even get sparser. And yesterday, Henry, you asked a question, right, about holes. They are the holes. And why do we get away with the holes? And we get away with the holes because you sparse grids and polynomial chaos and everything else only works if what you're building the surrogate or integrating is either the integrand is smooth, or if you're building an interpolant, the function you're interpolating is smooth. So you need smooth functions, and here's the needs for smoothness. So here's what happens if you try to approximate the integral of a discontinuous function using sparse grids. Here's the Monte Carlo results. You don't like this, but here is the sparse grid result. The exact value is 5.16771. So you need smoothness, and you can only get the accuracy that the smoothness allows. So there's a huge body of literature on so-called polynomial, global orthogonal polynomials, sparse grids, but they only apply to smooth functions. Now, I have to tell you from the analysis point of view, this is smoothness with respect to the parameters, to y. So when do you know that the solution is smooth with respect to y? Well, it's known for Poisson equation with a coefficient a that's linear in y, and that's about it. Is that true? Anybody correct me on that? Fabio, anybody? So we don't really know. It's very hard to prove. In fact, you can prove in that case that the solution is analytic in y. But for most other PDEs, nonlinear ones especially, you just have to hope that it's smooth. And yeah, people use it all the time, and you get good accuracy, so it is smooth. Okay. So multi-level and multi-fidelity. How much time do I have? Not much. So I'm going to skip multi-level and go to just a few words about multi-fidelity. So multi-fidelity takes advantage of, you have many different models available for for many different surrogates available to you. Interpolants, least squares, reduced order models, etc., coarse grid approximation, and they're very different from each other, and with respect to cost and fidelity. And there's no hierarchy here because these can be anything. So all we assume about these models is that we know the costs of each model. How much does it cost to run one of these models? What we have to do in a nutshell, I don't have enough time to go into details. There are not that many details here anyway. We have to do a few expensive runs to estimate the correlation between these models. Because that establishes a hierarchy, and then we can apply these multi-fidelity models. So, but at the beginning we don't know anything about the relative fidelities, but we will do a little bit of expensive work to find out the correlation between the different models. And I won't tell you any more, but here's what happens. So here is a numerical experiment. So we have 6 models, a high fidelity phi-element model, 300 degrees of freedom, that's our high fidelity. That's our truth model. We have a POD model with 10, 5, and 2 degrees of freedom, support vector machine, and an interpolation using 256 points. So there's a damage plate. And here is the variance and the mean square error for several model combinations. If I just use one model, Monte Carlo, that's the red thing. If I use 2 models, I get down to the green. And so what does this select? So the whole idea of multi-level and multi-fidelity is that you do a lot of sampling on your cheapest model, and you do very little sampling on your expensive models. So here's the breakup of what happens. With one model, you do all your sampling on the expensive model. You do Monte Carlo on your most expensive model. By the time you do 6 models, 98% of your sampling is on the cheapest model, and a very, very small number of samples are done on your expensive model. So that's why you get that kind of behavior. And here's another example of a limit cycle oscillation, where again we have 4 models here, and you see sometimes they're diminishing returns. One of the things about this multi-fidelity approach is that sometimes things are not correlated to the expensive model. That tells you shouldn't be even using that model at all, because it's not going to help you. I just want to say a few words about compressed sensing, because that's one of the modern approaches. We have experts out in the audience, so they can volunteer to answer questions about this. So what is compressed sensing? This comes from the signal processing community. So everything I talk about, the approximations a priori don't know anything about the function being approximated. You have sparse grids, you have you have global orthogonal polynomials. Those basis functions have nothing to do with are not informed by the function you're approximating. So what is compressed sensing here? Well, what you do is you have an underdetermined system. So think of this as you oversampled and you have an underdetermined system. You have a vector. You want to determine this vector, this long vector on the right, but you've got this rectangular matrix. So what you do is you try to say, well, there's lots of solutions to this matrix problem. There's lots of solutions. We want to invert that matrix, so to speak. We want to find that long vector. And so compressed sensing says, let me try to find a solution where lots of those entries in that matrix are 0. In that vector are 0. And why that's important? Because for us, that vector are going to be the coefficients and the polynomial expansion of what we're trying to approximate. So this is going to tell you that a lot of terms in that polynomial expansion aren't important for this particular application. So that's what compressed sensing is about. And it's basically, instead of doing least squares, you like to do so-called L0 approximation, but usually you can do it with L1 approximation instead of L0 approximation. And this is because you can see that this is a picture that shows if you do L1 or L1/2, those are the balls in L1 and L1/2, and your blue line only touches one point, which means the other coefficient, right on the axis, which means the other coefficient is 0, while L2 approximation is going to be tangent, so it means both coefficients are non-zero. And so this is what you get. So that's all the time I have to say about compressed sensing, but this is one of the very exciting things happening, because now the whole idea is to have less degrees of freedom than total polynomial. Everything I talk about is, if you want a certain degree of approximation and you don't use a method that has something to do with that is informed by the function you're trying to approximate, you can't do better than total degree. If you want to do better than total degree, you have to use a method that takes information of the function you're being approximated, so to get fewer degrees of freedom, and that's what compressed sensing and several other approaches do. Thank you. And wait a second. I should say, I have a concluding slide. We're never going to know how many licks to the center of the pop. And here's my favorite quote of all. Now questions. Oh, well, questions. Or we can do this over a bidder. Over a bidder.
Don't worry, we have got time. Don't worry.
Oh, too bad.
I do want to ask you a question.
Yeah.
All right, thanks.
I have a comment, or two comments. One is to you, where you explain KL expansion and how you make the inputs to the PD. Maybe you can put that slide up again. The very beginning of the talk.
Do I want to put it? Oh. KL expansion, huh?
How you get uncorrelated to independent variables.
Yes. Did I?
But
Yeah, somewhere here.
no, I think one back in
The other way.
other way. Right, so I don't think they think with the CDF will make them independent, but of course you can
No, no.
expand the uncorrelated coefficients just to tease you in polynomial chaos in independent variables, and that's how many people do it. So it's a way of using.
No, yeah, polynomial, yeah. But this is not polynomial chaos. Yeah, polynomial chaos.
The uncorrelated coefficients. So the coefficients are correlated, but you can use polynomial chaos for the uncorrelated coefficients, and then you have it in independent random variables.
Okay.
If I may add another comment where you compared, I think it was in stochastic hierarchy, full tensor product.
Yeah.
I think you said the full tensor product is no good. I think it is good in some ways, because then the coefficients and everything are really tensors, and you can use sparse tensor representation. And that makes it much faster, even though the number of degrees of freedom grows, it makes it much faster than the other one.
Listen to him.
Yep.
Hi, thank you. I might have completely misunderstood, but I think I'm getting applied maths now, so thank you. I just had two things. What do you need to know about your simulator before you choose your finite elements or anything like that? Do you literally know nothing and then you use something to find out? And then how do you validate your methods?
What defines simulator?
So if I had, well, it's hard.
You mean a simulator in parameter space?
So you showed one example and you, just at the end you showed your example with some bending or something.
Yeah.
And that I guess came from an engineering model.
Yeah.
How much do you need to know about that engineering model before?
All you need to know is somebody to give you a code that produces the solution for given a value of y of the parameter vector, produces a solution. That's all you need to know.
So you're assuming the smoothness, but then how do you check that at the end?
Well, you have to do some kind of refinement studies or something like that to make sure you're getting some kind of convergence rate. But I mean, yeah. Smoothness in y, I don't know how to do, but I don't know, maybe somebody else here knows how to do.
Maybe just to step in, I think you were trying to play devil's advocate. I think it is often smooth.
Yeah, no, it
I
is.
mean, it is. You were just saying it's not theoretically true.
It's not theoretical. No, that's why I did say that it works in many settings, so it is often smooth. You just can't prove it.
Yeah.
But if you want to verify that it's smooth, you should be able to show that you increase the number of sample points, for example, that you're getting the convergence you expect.
Okay.
I just had a comment and a question about something that came towards the end on multi-fidelity modeling. Multi-fidelity is kind of a sort of trendy thing in the applied math community at the moment. It sounds like a really nice idea that you can do something where you have really complex applications where you have a wide variety of different models. And speaking to some of the statisticians here, that's the kind of scenario that they have as well, in particular things like climate modeling and things like that, or perhaps other things as well. So I think that ought to be an area which is ripe for discussion between both sides of the community. That was a comment. But I had a technical question. In the papers that I read on this subject, very nice, and they kind of say we can use a really wide variety of models and don't need to make any assumptions on the approximation errors for each of those models. But the key thing you said is you need to be able to estimate the covariances between the outputs of the different models that you have. So my question was...
Let me correct myself. You always have a truth model. There's one model that you want, just like in multi-level Monte Carlo, there's one model that you have accepted as the one you want the solution for, and the other ones are just cheaper models. So the correlation is only with each model with the truth model, but go ahead.
But can't your estimates of the correlation or covariance be polluted by the errors between the truth and each of your models that you're using? And if you get your, or basically, more general question, if your estimates of the covariance are really inaccurate, does that screw things up quite a lot?
Well, yeah, sure. But I can't prove this, or there's certain robustness, because you don't have to get it exactly right, but if you're way off, yeah, sure. But that means you just waste it won't be as efficient as it could be if you had very good knowledge of the covariance, but I don't think it'll kill it, it'll just make it less efficient.
I had a comment, because we're touching on, or we're going to talk about quasi-Monte Carlo in the next talk as well, I guess, is I think I made this comment on your slide before. As you say, for stochastic collocation, you can use knowledge about the importance of the parameters to do anisotropic stochastic collocation.
Yeah.
And I think this old theoretical result about the log q to the n coefficient in your quasi-Monte Carlo is, especially for the application you're presenting, is an artifact, a theoretical artifact. I really think quasi-Monte Carlo do not see that log q to the n, because parameters are we're not putting white noise into
they're not isotropic, yeah. Well, the other problem with that estimate is that that's the estimate for n large, you know.
No, but I mean, what there is theoretical results, arguably for only simple model problems like the diffusion equation, that prove that there is no, even that you can
there is no
very
large term,
and get from n. That's what I was going to say. Okay, any other questions or comments? In which case, we're even early for coffee. Enjoy, and see you. Yeah, thank you.